So I basically left off by describing this sort of pioneering experiment on optical molasses. And the result of this experiment is they got a temperature that was in agreement with the theory, this sort of simple Doppler cooling theory. But the large uncertainties in the measurements at Bell Labs led to several other groups to actually look at optical molasses in more detail and try to come up with different techniques for measuring the temperature. So one of the early experiments was done in Bill Phillips' group, where instead of using this release and recapture method that was used at Bell Labs, they did a time of flight measurement. So they set up their optical molasses, this nice bright cloud of atoms that you see here. But below that, they put a sheet of light, which is shown in this cartoon here. And what you do is, when you shut off the light from the optical molasses, the atoms will fall under the influence of gravity and will pass through this sheet of light. And this sheet is thin compared to the extent of the cloud here. So what you do is you look at the fluorescence coming out as the atoms pass through this sheet of light. And because this, so one thing you get is you know the transit time for the falling atoms because of gravity. But because the atoms have this finite temperature, the cloud's expanding as a function of time. And so by looking at the width of the distribution, or the amount of time it takes for the entire cloud to pass through this sheet of light, you can learn something about the velocity or momentum distribution of the atoms. So when they did this experiment, they actually got a curve. The data points here show the curve that they got from this time of flight method. And so their best fit to this corresponded to a temperature of 25 microkelvin. This is the curve that you would expect to get if the atoms were at 250 microkelvin, close to the temperatures measured at Bell Labs. So clearly, this is showing temperatures much lower than what's expected or what was measured in the Bell Labs group. So you're getting temperatures much colder than the Doppler limit. Just an interesting side note on this experiment: when they first set up this experiment, they put the probe beam above the sample of atoms. And because they figured, well, 240 microkelvin, they calculated when the atoms should pass through. And when they actually tried the experiment, they didn't actually see anything. And that's because the atoms were so cold, they never actually made it to the probe beam right above the clouds. And then when they finally put the probe beam below, they could actually see something. So the problem is that they were getting temperatures for their optical molasses that were much colder than expected. In other words, optical molasses was working much better than it should have. So this is one of the few examples of violation of Murphy's law in the laboratory. Normally things go the other way. They don't work quite as well as you'd like. And it couldn't be explained by simple Doppler cooling temperatures. So here's some data they took on the temperature that they measured as a function of detuning. So whereas the simple Doppler cooling theory showed that they should get to a minimum temperature at exactly a detuning of half alignment from resonance for sodium that's at 5 megahertz, they found that as they detuned the laser further and further, they got to even colder and colder temperatures. They made other sorts of measurements which found that the temperature is actually proportional to the intensity. And if you remember from the simple Doppler cooling theory, the temperature only depended on one parameter, and that was the excited state lifetime of the atom that you're working with. So they found that the temperature was proportional to the intensity. They also found that the temperature was very sensitive to the laser polarization, unlike the case for the simple Doppler cooling theory, which had no information about the laser polarization in it. And as a result, it was also very sensitive to magnetic fields. So to get to these very low temperatures, they had to make sure that the magnetic fields were zeroed out. So they used coils to cancel out, for example, the Earth's magnetic field at the milligauss level to get down to these temperatures. This suggested that maybe the magnetic sublevels in this system are important, or in other words, this is a multi-level effect. In the previous, in the Doppler cooling theory, we only considered a two-level atom, an atom which had a ground state and an excited state. This seems to suggest that there are other energy levels involved in the system, in particular the magnetic sublevels. So to understand this, a number of people thought about this problem, including Claude Cohen-Tanucci. At the same time, there were also the experiments done in Paris in the group led by Cohen-Tanucci, which also saw subdoppler temperatures. One of the nicest way to approach this problem is to consider sort of the dressed atom approach of Cohen-Tanucci, which you can learn about in some of his textbooks. But basically, what you want to do is you have this two-level atom with the ground state and an excited state, and you want to couple that atom to the radiation field, which is at frequency omega sub L. And this is the radiation field corresponding to having n photons in the field, and if you go down one unit of energy, omega sub L, you have n minus 1 photons. Alternatively, you can go up and have n plus 1 photons. So the field actually consists of a ladder of states, all separated by each adjacent state separated by omega sub L, corresponding to the addition of another photon. So the sort of the bare system involves the atomic states, the ground state and the excited state, and this photon field. But if you actually couple them together, you generate new states, using this notation 1 and 2 here, which are shifted from the bare states. So here, if you look at what the energy of the state, for example, corresponding to the ground state and n photons, it's at a slightly different energy corresponding to the excited state here and n minus 1 photons because of there's a detuning between the atom's resonant frequency and the laser. So there's slight energy offset. But if I actually couple these two states together with some intensity given by the Rabi frequency here squared, then there's a shift in the energy levels. And you end up with these new basis states of 1 and 2 here. And so now you generate a ladder of states which alternate between these two coupled states, 1 and 2. And these energy states are shifted, and the shift depends on what's called the generalized Rabi frequency, but it depends on the square of the intensity and the Rabi frequency squared. So it's easy to understand now sort of the dipole force in this picture. If I have a gradient of the intensity, which means that there's a gradient of the Rabi frequency here as a function of space, then in the dressed atom picture, what I have is I have my basis states, 1 and 2, which asymptotically with zero intensity would correspond to a ground, in this case, a ground state and n plus 1 photons in the field, or a state corresponding to the excited state and n photons in the field. And because there's a relative frequency difference between the laser and the atomic transition, you have a detuning here. So what happens in this process of absorption followed by spontaneous emission is that atoms that are predominantly in the excited state will, by spontaneous emission, will end up mostly in the ground state. And so in the case where I have a detuning greater than 0, what this does is it takes any population that's mostly in the excited state and puts it into the ground state. So you find that most of the population of the atom is in this state, which asymptotically corresponds to the ground state and n plus 1 photons in the field. As a result, because the energy level of this state shifted up as a function of intensity, you find that for detunings greater than 0, you end up with a net repulsive force, a force that's pushing you away from the high intensity. Alternatively, if you look at what happens when the detuning is less than 0, you end up with a shift of the energy levels and a population imbalance, such that, again, atoms are mostly in the ground state, such that the atoms are attracted to the high intensity region. So you have this energy shift that results in the energy being lower at the high intensity region. So you can go through this calculation in more detail, and what you find is that the energy associated with this light field, for example, the peak of the intensity, or if you want, you can make the intensity as a function of space. If you take into account the population imbalance resulting from spontaneous emission, you find that the potential of the energy shift has this function here, which for low intensity and large detuning, you find that the intensity goes like, the energy goes like the intensity or the Rabi frequency squared divided by the detuning. So this is basically just the AC start shift, and it's what's responsible for the gradient force or the optical dipole force. So again, the dipole force is attractive for delta less than 0 and repulsive for delta greater than 0. So this dipole force is one of the main ingredients responsible for the low temperature. And in fact, a more detailed analysis taking into account all the magnetic sublevel of the atom and optical pumping between the various magnetic sublevels led to this explanation called polarization gradient cooling, or cooling due to this thing they call the Sisyphus effect. So I want to consider an atom which has a transition going from J equals a half to J equals 3/2. So in other words, the ground state has two magnetic sublevels, M equals -1 and M equals +1/2, and the excited state has 4 sublevels. In the presence of two counterpropagating laser beams which have, for example, orthogonal polarization, so the polarization of one beam is along, in this case, the x-axis, and the other one's along the y-axis. These two the superposition of these two waves with orthogonal polarization creates a polarization gradient in space. So in one place, the polarization is vertical. If you move to another place, it looks circular, and if you move again, its polarization is linear but pointing orthogonal. And then if you move another quarter of a wavelength, you get the opposite circular polarization, and so on. So as you move, and this process repeats every lambda, every wavelength. As you move in space by a wavelength, it repeats itself. So you find that in space, the polarization is constantly changing. As a result, you find that these magnetic sublevels are shifting as a function of space. So at one place where the laser will actually couple the M equals, the polarization of lasers such that it will couple the M equals -1/2 state to the excited state stronger, then you find that there's a big shift in the energy of the atom at that position. And then as you move to a new location, you find that the other state, now you have the opposite circular polarization, so the other state, M equals +1, gets shifted. So you have this basically sinusoidally varying shift in the atomic energy levels as a function of space due to this polarization gradient. Another way to look at this is if I take these two counterpropagating laser beams with orthogonal polarization, it basically corresponds to the superposition of two optical standing waves, one which has right circular polarization, the other which has left circular polarization. But the basic idea now is that an atom initially in one magnetic sublevel, well, if it's moving, will see a potential hill and start slowing down as it moves up this potential hill. And when it gets to the top of the potential hill, where the energies, the intensity is such that it'll optically pump into the other state because of the change in polarization and end up in the other magnetic sublevel, where the energy is now minimum again. And the atom in that magnetic sublevel will still moving, will roll up a hill, lose energy, and again, when it gets near the peak here, it will optically pump into the other magnetic sublevel, and so on. And so this reminds you of the myth, the Greek myth of Sisyphus, who had to constantly push a rock up a hill, because every time he got to the top, it rolled back down. In this case, the atom's moving up the hill, and it loses energy, but when it gets to the top, it ends up at the bottom of the well again, and starts to start climbing back up again, and loses energy. So many such processes, many such cycles of this process of optically pumping from one state to the other state and climbing up a hill in between will result in an energy reduction of the atom. If you do a detailed calculation, this was done by Cohen Tanuki and John Delibart and also Steve Chu, you find that the temperature, the final temperature that you get to just depends on the light shift. So it depends on basically the depth of this potential well that the atom has to climb out of. So it's actually proportional to the intensity, which the experiments in this showed. And it's also inversely proportional to detuning. So again, if you make the detuning larger, you end up at a lower temperature, which is also what they saw in the data at NIST when they measured subdoppler temperatures. Now the final cooling limit you can get to in this process is basically limited by the recoil energy, because each one of these transitions involving climbing a hill and optically pumping to another magnetic sublevel involves the emission of a photon by spontaneous emission. So ultimately, the final temperature you can get to just depends on momentum diffusion associated with spontaneous emissions. So you can't get to any lower than the recoil energy. But that's still pretty cold, because if you remember some of the numbers I gave earlier, for sodium, the recoil energy is about 1.2 microkelvin. And for cesium, it was even about a factor of 10 less, it was on the order of about 100 nanokelvin. So you can get to very low temperatures. In fact, in practice, though, you don't actually get to the recoil energy with this. You get on the order of maybe 3 or 5 times the recoil energy. But that's still quite cold, especially compared to the Doppler temperatures. There are techniques to actually cool below the recoil limit. I won't talk about this in any detail, but the basic idea is that what you want to do is you want to take an atom, and when it has a low enough velocity, you want to somehow hide the atom so it doesn't scatter any more photons. Because if it scatters a photon, then there's a chance that it will pick up, even if it's at, for example, if it's at zero velocity and it scatters a photon, then by the sort of random spontaneous emission process, it could end up with h bar k of momentum. And so what you want to do is you want to be able to hide the atoms that are at low velocity so they're not excited anymore. And there's a couple, this technique is called velocity space optical pumping. It was first discussed by Dave Pritchard in a conference proceeding, but it was actually implemented by Steve Chu in a process called Raman cooling, where basically using narrow line-width transition, you could make the Doppler, you could make the transition very Doppler sensitive so that you didn't interact with the zero velocity of the atoms or the atoms close to zero velocity. The other alternate way to do this is to use a process called velocity space coherent population trapping, also demonstrated in Cohen-Tanuji's group, where basically you use quantum coherences to generate this sort of narrow excitation feature. But using this technique, people have gotten to, well, using Raman cooling, for example, in Chu's group, they've gotten to temperatures that are on the order of about, I think maybe about a factor of 50 or so below the recoil energy in one dimension. But when you scale it up to 3 dimension, it becomes harder and harder to keep atoms localized in this one small velocity group. So I think they can get to just under the Doppler, just under the recoil energy in 3 dimensions. And same thing with the other technique demonstrated in Paris. There is a technique, though, that actually works quite well for cooling below the recoil limit. And I'll mention this briefly because it's used extensively for producing Bose-Einstein condensates, which I'll discuss in an upcoming lecture. But this process doesn't actually involve any scattering of light by the atoms, because, as I mentioned, scattering of light leads to a final temperature limited by the recoil energy unless you do something clever to get around it, but even then it becomes very restrictive and difficult to use. And the basic technique was quite simple and was proposed by Harold Hess back in the early 80s in the context of cooling spin polarized hydrogen. And it's a process called evaporative cooling, and most of you are familiar with it. It's basically, if you have a hot cup of coffee and you leave it on the table for a while, what happens is the hot atoms leave the cup, and as a result of the remaining atoms in the cup rethermalize to a lower temperature. So the way you actually implement this for neutral atoms is you want to trap the atoms in some sort of potential, preferably some sort of conservative potential, where the atoms are sort of just rattling around with some energy. And then you want to lower the height of the trap so that the hot atoms can leave. And so in other words, what you're doing is you're taking the initial energy distribution of the atoms, and you're allowing part of it to leave, or you're cutting out part of this energy distribution. And then what happens is the atoms, by collisions, will rethermalize through a thermal distribution given by a lower temperature, because you've basically removed some of the atoms from the higher energy portion of this distribution. And as you keep lowering the height of this barrier, you get the lower and lower temperatures. The way you actually implement this in a real experiment is you have your atoms in a magnetic trap, and you use radio frequency transitions to take them from a state where they're actually trapped to an untrapped state. And so evaporative cooling, because it doesn't involve scattering of photons or anything, basically has no lower limit except for the ground state energy associated with your trapping potential, which can be quite low. And so it's actually the preferred technique used to achieve Bose-Einstein condensation, which I'll discuss a little later. So let me now mention something about traps for neutral atoms, since I brought up a technique that actually uses a trap. Unlike ions, coupling to neutral atoms is very weak. So ions, if you can grab onto a charge with electric fields, you're talking about energies on the scale of electron volts. While with neutral atoms, it's several orders of magnitude smaller. You're talking about the type of energies on the order of microelectron volts. So trapping of neutral atoms had to wait basically until the development of techniques to cool atoms to very low temperatures, because it was just so difficult to make traps deep enough to trap atoms at room temperature, or even slightly lower, even at cryogenic temperatures. So there are a number of examples of neutral atom traps, and a lot of them were demonstrated in the early days of laser cooling and trapping. They're sort of fallen by the wayside. But there are still some that are quite popular and used extensively today, so those are the ones that I'll focus on. There are magnetostatic traps. These are traps that involve the interaction of the magnetic moment in the atom with magnetic fields. There are radiation pressure traps. These are traps that use the scattering force, so use radiation pressure to actually trap atoms. And one of the most popular ones is called a magneto-optic trap, or MOT. And then there are traps, optical traps that use the dipole force, the optical dipole force, or the gradient force, to trap atoms. And so it's the interaction of the induced dipole moment with the laser field. These are single focus beam traps, far off resonant traps, and optical lattices. So the magnetic trap was one of the first neutral atom traps demonstrated. Again, it relies on the fact that the energy of the atom in a particular magnetic substate depends on the strength of the magnetic field. So you see here that, again, I use one of my favorite atoms, sodium, as an example. If I have an atom in the F equals 2 hyperfine state, the ground state, 3s I have sodium, atoms with the magnetic, in the magnetic sublevel, given by MF equals 2, have their energy actually increases as a function of magnetic field. So if I can create a magnetic field that has a minimum in free space, then in principle, I can build a trap for atoms. Another way to look at this is the interaction energy of the magnetic moment with the magnetic field is just mu dot B, and so you can always create a force which due to the gradient of the field, which will result in a trapping force on the atom. Now it turns out that Maxwell's equations only allow you to create a magnetic field minimum in free space. So you can't actually have a magnetic field maximum in free space, which means that only certain magnetic sublevels can actually be trapped using magnetic fields. So basically, only the states where the energy increases as a function of magnetic field, in this case, M equals 2, MF equals 1, and this, or down here in the lower hyperfine manifold, the MF equals -1 state. Those are the only states that can be trapped using the magnetic trap. You can't trap the weak field steeping states. You can't trap those states that decrease as a function of magnetic field, the energy that decreases as a function of magnetic field. The main advantage of using magnetic traps is they're conservative. Or basically they're static potentials. Once you create a magnetic trap potential, you're not scattering photons or anything, so you don't have to worry about any, in principle, any intrinsic heating associated with trapping. They can be made fairly large volume. You can make magnetic coils whatever size you like, and so the traps can be very large volume. And they're fairly low cost. Basically, you just need to wind magnet coils and find sufficiently large power supplies to put current through them. But again, because you can't create a magnetic field maximum in free space, the main disadvantage is you can't trap the true ground state of the system. You can't trap the lowest energy state of the system. Well, this I just put it to show you that if you, the other plot showed you what happened in the Zeeman regime, where the the shift in the magnetic energy levels and the energy levels was just proportional to what M state you're in. People have built magnetic traps with very large fields, and so in that case you actually have to worry about decoupling the nuclear moment from the electron magnetic moment, which gives rise to the hyperfine interaction. And when you do that, you find that you basically end up with a family of states that either go down as a function of the magnetic field or go up as a function, whose energy goes up as a function of the magnetic field. And these correspond to just the electron states. In this case, for this alkali atom, it corresponds to either the electron pointing up or the electron pointing down. But again, there's only a finite number of states out of the total number of states that you can actually trap. So there are lots of configurations for making magnetic traps. One of the first ones demonstrated is a simple configuration called the quadrupole trap. And basically you take two currents, two coils here, and you run current in opposite directions. So maybe that's not drawn quite right. As a result, when you do that, what you want to have is you have the field lines that look something like this. So right in the middle, the field produced by one coil cancels the field produced by another coil. So you end up with a magnetic field 0 in the middle. And as you move away from the center between the two coils, you find that the field actually increases linearly as a function of position. So if I look at the magnitude of the magnetic field as a function of position in some direction, you find that it looks like this. And so this is the simplest design, but the major problem with this is you have a magnetic field 0 in the middle. And so in principle, you could lose atoms. So if an atom's in a particular spin state, it could pass through the magnetic field minimum and lose its identity with respect to what direction it's pointing in as it passes through, and end up in the untrapped magnetic substate and be lost from the trap. These are called Majorana transitions. And it's one of the major problems with using a magnetic trap with a magnetic field minimum in the middle. Despite this, this was actually the first magnetic trap demonstrated by Joe Phillips back in 1985, where he used Zeeman slowing to slow atoms down, and as the atoms got into the region of this magnetic field, he switched on the magnetic field and actually trapped the slowed atoms in this trap. If you're worried about the magnetic field minimum in the 0, then the easiest way to fix it is to put some sort of bias field, non-zero field in the middle. And the most popular geometry for this is called the Yaffe trap. In the Yaffe trap, what you have is you have two sets of coils here, which are running current in the same direction, so the fields add along the axis here. Yet, as you get towards the center of one of these coils, the field actually increases. So if you look at the field profile as a function of space, it peaks in the middle of the coils, drops down, but is non-zero in between the two coils. And then what you want to do is you want to add on a radial field profile that increases as a function of distance. And what you do is you basically create a quadrupole field in the radial direction using these linear current carrying bars. The resulting field that you create, the magnitude of the field that you create, basically has a constant magnetic field in the middle, so you don't have to worry about losses by passing through the 0 field region. And then you find that the field actually increases quadratically as a function of distance from the center. The main disadvantage of going into this geometry is it doesn't create as strong a field gradient as the quadrupole field. But that disadvantage is outweighed by the fact that you now have a bias field in the middle, which will keep you from losing atoms as they get colder and want to tend to localize in the minimum of the trap. So there's lots of ways to make this. People have used all sorts of different field coil geometries to create essentially this field profile. The other possibilities, in addition to using current carrying wires, people have used permanent magnets to create such magnetic fields, and even use microfabricated wires, wires on chips to create what they call chip traps. But here's an example from a group in Munich, a Netsch's group, which have created a magnetic trap on the surface. It's probably very difficult to see because it's so small, but there's a region there where they've created this magnetic field profile. So the Yoffie trap is by far the most popular geometry for magnetic trapping of neutral atoms, and there's various configurations, as I mentioned, various orientations of coils you can use to create this field profile. I'll mention one other type of magnetic trap basically for historical reasons, because it was actually the first type of trap used for creating a Bose-Einstein condensate. It's actually quite a clever idea. This is out of Eric Cornell's and Carl Lyman's group at GILA back in the mid-90s. So as I mentioned, the quadrupole field here has a magnetic field minimum, a zero of the magnetic field right in between the coil. And this is going to result in losses of atoms out to zero. So if I look at the field profile, it looks something like this. It's going to have a zero at the middle, and the atoms, as they get colder and colder, eventually they'll basically leak out the bottom of the trap in this 0 point. So what you want to do is somehow plug that zero, and one way to do this is to basically apply an external bias field, which shifts the location of this quadrupole field to a new location. And then rotate the bias field so that you take this quadrupole field at the new location and you're rotating it around as a function of space. And if you rotate things fast enough, the atoms will only see the time average potential from this rotating field. And as a result, you create an average field profile that has a non-zero value in the middle, because on average, the magnetic field is non-zero in the middle. And it's basically, for small expansions, looks parabolic. And so this is the time average field that you create by using this technique. It's got a bias field in the middle, and then it basically increases quadratically as you move away from the center. And as I mentioned, this was the first type of, this was the magnetic trap used to create the first VEC in the outline gas. What about electrostatic traps? Well, basically, you have the same type of interaction. You have an interaction that depends on the polarizability as well. If you have a permanent permanent electric dipole moment, then it's going to be just like the magnetic trap case, where you have the permanent dipole moment dotted into the electric field gives rise to an energy. But typically atoms actually don't have permanent dipole moments, so you have to induce an electric dipole moment using an external electric field. So if I have a static electric field, the atom has some polarizability, and you can induce a dipole moment in the atom. The interaction of that dipole moment with the electric field results in an energy. But it turns out that the sign of the energy, the interaction is such that you won't actually create atoms in the state where they can actually be trapped. So again, you run into the same problem with Maxwell's equations, that you can't create an electric field. You can only create an electric field minimum in free space. While it turns out for the induced dipole moment in an atom, you actually want the opposite situation. You want a magnetic field maximum in free space. So in general, you can't use electrostatic traps to trap atoms, neutral atoms. You can actually, if you have a molecule or something with a permanent electric dipole moment, you can actually use electrostatic traps, and this has been demonstrated by some other groups. So those are the type of static traps. So clearly one type of static trap is this magnetic trap. There are also traps that rely on radiation pressure for trapping atoms. So if we recall the radiation pressure on an atom moving at some velocity with the average force on the atom by two counterpropagating laser beams was given by this equation, which for small velocities could result in a damping force. So basically you get a force that's proportional to the velocity. On the other hand, for a trap, you actually want the force to be a function of position. So you want a spatially dependent force, not just a velocity dependent force. So the question is, how can I take this configuration and somehow make it position dependent? Well, it depends on the intensity of the light. So I can make the intensity of the light spatially dependent. One way to do this is to have, for example, diverging laser beams. So the intensity is stronger here compared to over here. Now, if I have two counter-propagating laser beams this way, then I find that, well, basically on the symmetry line here, there's no net average force acting on the atoms. It will scatter light equally from both beams. But as I move towards one of the beams, what happens is it sees a higher intensity from one beam compared to the other beam, and so it'll tend to scatter more photons from the counter-propagating beam, which pushes it back to the middle. Similarly, if I go off in this direction, you get a force that's trying to push it back to the middle. And so this is a way to actually make a position-dependent force. And so you can see in this simple picture that it would work. But what happens if I try to go beyond this one-dimensional picture and extend this idea into three-dimensional? Well, it turns out you can't actually do this. There's something called the optical Earnshaw theorem, which was put forth by Ashton and Gordon in response to some ideas about that people were proposing about using the radiation pressure for trapping. And the basic idea of the optical Earnshaw theorem is that basically you can't really have the photon momentum point only to one position. I mean, the photon comes in, but it's got to go out somewhere. In other words, the gradient of the Poynting vector has to be equal to 0. And this is analogous to the gradient of the electric field has to be equal to 0 for electrostatics. And so they call this the optical Earnshaw theorem because there's a theorem due to Earnshaw which says that you can't actually use point charges to trap a test charge of opposite sign by some configuration of point charges. This is sort of the equivalent idea in the optical domain. So the optical Earnshaw theorem applies to any situation where the atomic response is linear in intensity, as we saw for the two-level system, and the optical field is static. So basically you're not involving time average changes of the field. So one way to get around this is to go away from a two-level atom and to use a multi-level atom. And this is actually will allow you to circumvent the optical Earnshaw theorem and maybe even build a radiation pressure trap. And one of the most popular radiation pressure traps is the magneto-optic trap. And the basic idea was put forth by Jean Dalibard. It was never published. He mentioned it to Dave Pritchard at a conference. And Dave collaborated with the people at Bell Labs, Steve Chu and Art Ashton at Bell Labs, and got this trap working there. And the basic idea is this. Suppose I have an atom, for simplicity we'll pick one that has J equals 0 in the ground state, so it has only one energy state, sublevel in the ground state. And the excited state, J equals 1, so there's 3 excited state sublevels here, characterized by M equals -1, 0, and +1. Now if I send in light and it has circular polarization, it has one circular polarization will take the atom from the excited state and drive it up to the M equals +1 state. The circular polarization, the opposite circular polarization will take an atom in the M equals 0 state and drive it to the M equals -1 state. So now what I want to do is consider a situation where I have a gradient of the magnetic field. So I have a magnetic field gradient that's linear, passes through 0, but increases linearly as a function of position. And one way to do this, for example, in 3 dimensions, is to use a quadrupole field. So as I mentioned, a quadrupole field is 0 in the middle and increases and points in one direction as you move away from 0. And if you go in the other direction, it also, through small displacements, increases linearly, but points in the other direction. So an atom in the presence of this magnetic field, the energy levels of the atoms, according to the Zeeman effect, will be split. So this would be as a function of space, or alternatively as a function of magnetic field. And so you see that if I send in 2 counterpropagating laser beams with opposite circular polarization relative to a fixed axis in space, then an atom moving off in this direction, in the plus d direction, will encounter a counterpropagating laser beam with the polarization that wants to excite it up to this state corresponding to the lower state, or in this case, m equals -1. Alternatively, if it moves in if it moves in the other direction, it'll see a counter-propagating beam with circular polarization, which wants to excite it to the n equals +1 state. So if I choose a detuning that's less than the resonant frequency corresponding to the zero magnetic field case, then what will happen is as the atom moves off in this direction, it'll be more in resonance with this laser than this laser, because this laser has sigma plus polarization with respect to the local quantization axis here. And so it wants to excite the atoms up to this state, but that's further away from resonance than the laser frequency here. So as a result, the atom will scatter more photons from this counter-propagating beam than from the co-propagating beam, resulting in a net force pushing it back in the -z direction. And similarly, if the atom's moving off in this direction and the laser detuning's less than the transition to zero field, it'll scatter more photons from this beam than this beam, which actually wants to drive it up to the n equals -1 state here. So now what you have is you have a force that depends on position, or in other words, you have a detuning that depends on space because of the presence of this magnetic field gradient. So if the magnetic field gradient is linear here, so the magnetic field is just proportional to the displacement, then what you want to replace, what you want to do in the Doppler cooling force, or the force on the atom acting in the presence of these two counter-propagating laser beams, is replace the Doppler shift kV by a term now that includes the Doppler shift, which is still there because the atom's moving with some velocity, but also has a term which accounts for the change of the resonant frequency of the atom as a function of space. And when you do this, if you plug this in and you do an expansion for small velocities and small displacements, you find that the average force acting on the atom due to the two counter-propagating laser beams has a term which results in damping, or is proportional to velocity, but also has a term that's proportional to position. And so for an appropriate detuning, this will provide a restoring force, pushing the atoms back to the middle, in addition to a damping force. And so you can extend that idea easily into 3 dimensions by one, using a quadrupole field to create a linear increase of the magnetic field from the center. So the magnetic field is 0 in the middle and increases linearly as you move away from the center. But then you just choose the appropriate laser beams from your set of counter-propagating laser beams so that it excites the atoms predominantly from the counter-propagating laser beam as it moves away from center. And this trap was demonstrated in a collaboration between the group at MIT and Bell Labs in 1987. The experiment was actually performed at Bell Labs in Steve Chu's group. And what's nice about this is not only is it a trap, but it also has cooling built into it. In particular, it has this, because you have a magnetic field 0 in the middle, it actually has even sub-Doppler cooling built into the middle, which was demonstrated earlier with just counter-propagating 3 orthogonal pairs of counter-propagating laser beams. So here's an example of an apparatus from a Mott magneto-optic trap from the apparatus that I used to work with. And there, what you can see in the middle is a small cloud of sodium atoms, so this little ball of atoms in the middle corresponding to atoms held in this magneto-optic trap. These are the coils that I used for the magneto-optic trap there. And there's a set of laser beams coming from the various directions, as well as the slowing laser from this direction. So the magneto-optic trap is sort of the workhorse trap of the laser cooling and trapping community. And typically you get densities on the order of 10 to the 10 or 10 to the 11 atoms per cubic centimeter. People have built traps that have trapped up to about 10 to the 10 atoms. And you get the temperatures on the order of millikelvin. If you're sometimes careful about it, you can even get sub-Doppler temperatures, so some millikelvin temperature atoms in your magneto-optic trap. The other type of trap that people use is the optical dipole trap, as we discussed earlier, and that's basically, again, it's this trap the potential is due to the AC start shift, or the optical dipole force. And so you induce a dipole moment in the atom, which interacts with the external electric field. And so, again, just as you would for optical tweezers, you can actually trap atoms at focused laser beams. And so you find that the atoms are actually trapped in the intensity maximum if the detuning of the laser is less than the atomic resonance. And alternatively, if the detuning of the laser is greater than the laser frequency is greater than the atomic transition frequency, you create a repulsive force, and so atoms are repelled. This type of trap was actually first proposed by Ashkin back in the mid-70s, I believe. But it really had to wait until the development of laser cooling to actually demonstrate that it worked. And so the first demonstration of this trap was done at Bell Labs, where they used optical molasses. So they had atoms in optical molasses to load the trap. And it turned out that it was also the first, I believe, the first color picture that appeared in physical review letters. Although if you look at it, it's really hard to see the trap. So one of the things, so this first trap that they demonstrated was certainly detuned. It was red detuned from the atomic resonance, so the laser frequency was less than the atomic frequency, but it's still fairly close to the excitation frequency. And so as a result, there was actually a lot of heating in the trap because the atoms, even though it was very far off resonance, or quite far off resonance, it was at a fairly high intensity, so the atoms could keep scattering photons. And so they had to actually continually cool the atoms with optical molasses to keep them trapped in this trap. It turns out that you can actually use the same idea, but detune the trap even further and create what is effectively a static potential for the atoms, or a conservative potential for the atoms. So, and the reason you can do this is that the photon scattering rate is proportional to the intensity, but goes inversely proportional to the detuning squared, while the depth of the trap, which depends on basically the AC start shift, only goes like 1 over the detuning. So if I make the detuning large enough, I can reduce the photon scattering rate to a point where it's sort of negligible on the time scale of your experiment. Yet, I can create a trap with sufficient depth just by increasing the laser intensity. So this laser trap, in contrast to a MOT, is essentially a conservative potential, and people call it far-off resonant trapping, or FORT for short. The major disadvantage is you often have to go to very, very large detunings to get the photon scattering rate down. As a result, this start shift here is quite small, and so the traps are not very deep. But they're used quite extensively with ultra-cold atoms, in particular DECs, because those atoms are at very, very low temperatures and you don't actually need very deep traps. So I want to mention one application of far-off resonant trapping, which hopefully I'll touch upon some more in a subsequent lecture. But one particularly nice application of far-off resonance trapping is something called optical lattices. So if you take two counterpropagating laser beams and you interfere them, what you create is an optical standing wave. So you create an intensity pattern that's sinusoidal in space. And it turns out, depending on the detuning, whether you're positive or negative, you can actually trap atoms at the local minimum or maximum of the intensity. So in the case of I'm red detuned for this, I will trap atoms at the local intensity maximum. And if I detune far enough, this is basically a static periodic potential. And so you can put atoms in this, and you can even configure it in 3 dimensions, so you get 3-dimensional trapping. And what you've done is you've basically created a 3D optical a lattice of atoms. And there are ways, which I'll explain a little later, about how to load basically 1 atom per well in this, sort of configuration. And so this is a starting point for a lot of experiments these days using ultra-cold atoms. Because this basically mimics a system that you have in solid-state physics, namely a periodic potential where you have electrons confined by a periodic lattice. So getting close to Andrew. That's it. So I think maybe this is this is a good place to stop here. And so when I continue on the subsequent lecture, I'll actually get into the BEC and the applications of those Einstein common physics. Thanks.
Question?
For the trap that Wyman and Cornell used, how fast do you have to spin those traps?
So they had theirs spinning at about 5 kilohertz. So that's basically you want to make sure that you spin it fast compared to the natural oscillation frequency when you create that trap. And so if they were getting oscillation frequencies on the order of a few hundred hertz, and so you want to go easily 10 times faster than that. And of course, the oscillation frequency depends on the mass of the particle that you're trapping. In their case, they have rubidium, which is pretty heavy. We actually built one where we trapped sodium, which is lighter, and so we had to spin ours at 20 kilohertz, which is technically a little more difficult, but it has the advantages. It's outside of your hearing, so you don't hear this. In their case, you can actually hear the thing whining at 5 kilohertz. Unless you're a dog.
Any other question? Okay, so let's take a break.